Hi girls, in today's video I'm going to finish section 11.3 using the coordinate axis in trigonometry that we didn't have a chance to finish in class. So let's take a look at the types of angles we were looking at before. It says now let's look at this angle. This angle is in the second quadrant. Prior to this all we did was look at acute angles that fell within the first quadrant. So this means that these angles are obtuse. If they fall in the second quadrant, they're going to fall between 90 degrees and 180 degrees. So in our unit circle, our obtuse angles would fall in the second quadrant. So when we're working with an obtuse angle, sometimes it's a lot easier to think about the angle that it relates to in the first quadrant. What acute angle does it relate to? What do we mean by that? Let's look at this diagram in a different way. If we look here at this obtuse angle, we can relate that to the acute angle that's in the first quadrant. So we're saying here that this acute angle is 30 degrees, which means that this angle in yellow, if the entire angle from the first quadrant all the way to the x-axis in the second quadrant is 180, and this angle is 30, that means that this yellow angle is supplementary to this angle. So we take 180 minus 30, and that gives us 150. So in this case, our theta is 150 degrees. We were given that this was 30. So we knew that this was 150. Now, it's easy for us to work with the 30-degree angle in the first quadrant. Here's our B value, here is our A value, and we even did one of the examples before about how to work with that. So let's take a quick look at that angle. So this is what we just talked about. As you can see, we can calculate the value of B as we did before. We know that B is the cosine of 30 and that Y is the sine of 30. So if we look at the relationship of B in the first quadrant and C in the second quadrant, we notice that they are a reflection of each other over the x-axis, which means that their y values have remained the same, but the x value has gone from being positive to being negative. So the angle measure of the obtuse angle, 150 degrees, if we want to find the value of point C, it's going to have the same y value, so it's going to be the sine of theta, and the x value is going to be the opposite. So we're going to have the cosine of theta, and in this case it will be the opposite of the cosine of theta. So what does that really look like? We've said before that B is equal to, or the coordinates are the cosine of theta, cosine of 30, sine of 30. Which we found to be, in a previous example, the square root of 3 over 2, 1/2. So we know that the coordinates of point C would be the cosine of 150 and the sine of 150. But based on the fact that it is the supplement of 30, it's also the opposite of the cosine of 30, sine of 30. All right, so it's a little bit difficult to understand when we're dealing with these supplementary angles. And since we already know these values, all we have to do is say that C then is the opposite. So it's the opposite of square root of 3 over 2, and the sine value stays the same. So without any further calculation, we were able to take the coordinates from B and turn them into the coordinates at C. All right. So this is very fundamental to what we need to start doing with, in the rest of trig. So here's the rule. For supplementary angles, alpha and beta, supplementary angles, okay, they have to be supplementary. The sine of A always equals the sine of B. And we saw that here. This distance, the vertical distance here, is the same as the vertical distance here. So it's always going to be the sine of the acute angle. The sine of the acute angle, in this case 30. And the cosine of alpha, the acute angle, is equal to the opposite of the cosine of beta. So again, we take the acute angle, the cosine of alpha, and it's going to be equal to the opposite of the cosine. Another rule, and these seem a little bit tough to understand right now, I understand that. For any angle theta, the sine of theta is going to be the same as the sine of the complement, the supplement, 180 minus theta, right? Sine of 30 is going to be the same as the sine of 150. We saw that up in our example here. The cosine of theta is going to be the opposite of the cosine of its supplement. So the cosine of 30 is going to be the opposite of the cosine of 150. So let's take a look and do some of the examples in exercise 11E. So it says use the diagram to find the coordinates of point B and point C. For the given values of theta, give your answers to 3 significant digits. So the first example says theta is 30, and we've done that. Since it's asking us to do it in 3 significant digits, we're going to be using our calculator for that. So for A, we're going to find for point B, it'll be the cosine of 30, sine of 30, which is going to, oops, I don't know why I wrote D, which is going to give us 0.866 and 0.5. Let's try B. Theta is 57. Oops, I forgot to do C here. Let's go over here. I forgot to do C. So in this case, if B looks like this, for C, my sine value stays the same, but my B, or my x value, my x coordinate, becomes the opposite of what it was over here. All right, so now let's do B. 57 degrees. So for B in this case, I'm going to find the cosine of 57 and the sine of 57. And once I do that on my calculator, I find that that's going to give me 0.545, 0.839. So what does that mean for point C in this case? It's the opposite of the cosine, and the sine stays the same. All right, so I want you to do C, D, and E for homework. So pause the video and go ahead and do those problems. All right, now that you're done with those, let's take a look at another example. We're going to be using the same diagram that we just used from example 1, and it says find the value of theta for each of the given positions of point C. Give your answers to the nearest tenth of a degree. So using this diagram, we're saying that point C has these coordinates. So how do we find those? Well, we take our calculator. For A, I have a cosine of negative 0.332. So that means I need to find the inverse cosine of negative 0.332. So when we do that in our calculator, we get about 109.4. So that means my angle measure is 109.4. And since that's an obtuse angle, I have obviously found 180 minus theta, which means in order to find the theta, I have to take 180 minus 104. So 180 minus 109.4 gives me 70.6 degrees. So that's my theta. Let's try one more together. B, I'm looking at the inverse cosine of negative 0.955, which gives me 162.7 degrees, which is an obtuse angle, which is this angle. So in order to find theta, I subtract that from 180. And that gives me 17.3 degrees. All right, so I want you to finish C and D for homework. Pause the video and go ahead and do that. Okay, the next thing has to do with finding the sine of each acute angle to 4 significant digits and then state the obtuse angle that has the same sign. So in this case, find the sine of each acute angle. If it's 15 degrees, we're going to find the sine of 15 degrees. And the sine of 15 gives us 0.2588. And the next part of the question says, state the obtuse angle that has the same sign. This is easy. We take 180 minus the 15 degrees, and that gives us 165 degrees. So you can go ahead and finish B, C, and D for homework. And then the last question says, find one acute angle and one obtuse angle value, or one acute and one obtuse value for angle A. So in this case, we have the sine of A and what it's equal to, so we need to find the angle measure. So again, we will take the inverse sine of what we're given here, 0.871, and that gives us approximately 60.6 degrees. And then to find the obtuse angle, I just subtract this from 180, and that gives us 119.4 degrees. So again, I want you to finish B, C, and D for homework. So pause the video and finish those. Okay, so the next section we're going to look at has to do with lines and unit circles. So let's recall when we have a line on a grid that the equation of that line is y equals mx plus b, but in this case the line is going through the origin, so our b is 0. So in this case it would just be y equals mx plus b. And the way we find the slope of our line is we find the difference in the y values divided by the difference in the x values. And we call that rise over run. Now, in the British books, in the international books, the word gradient stands for slope. So our book will always say gradient instead of slope. We'll usually say slope, but the more we talk about it, hopefully the more we'll start using the word gradient, and that way you'll be prepared for the IB exam. So in this case, the gradient of any line is the rise over the run. The change in the y values, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, or we can write it as delta y, the change in the y's, over delta x, with delta meaning change. Okay, so now let's look at what happens when we take that same line and we intersect it with the unit circle at point B. So I've taken my unit circle, which means this is my radius of 1 right here, and it intersects, or my line intersects my unit circle. So let's look at what we've got here. B is still going to be the cosine of theta, sine of theta, when we measure our theta here. My hypotenuse is still going to be 1 because it's one of the radii. The distance the change in the y values, or the length here, is going to be y, or sine of theta, and the length of this part of the triangle is going to be cosine of theta. So if we think about that, the tangent of theta, opposite over adjacent, so in this case the tangent of theta, as we know, is the opposite over adjacent, which in this case is the change in the y value over the change in the x value, and the change in the y value is sine of theta. The change in the x value is the cosine of theta. So we can now state that the tangent of theta is equal to the sine of theta over the cosine of theta. We can also state that the tangent of theta, if it's equal to the rise over the run, then we can also say that the tangent of theta is the slope or the gradient of the line. Okay, so tangent of theta is equal to the sine of theta over the cosine of theta, and the tangent of theta is the gradient of the line that intersects the unit circle with the degree measure of theta. So this leads us to three very, very important properties that we use in trigonometry for any angle theta. The first one is sine squared theta plus cosine squared theta equals 1. Now, let's take a look back at that particular angle and figure out how this works. Well, if we look here, the property number 1 that we just talked about is also known as the Pythagorean theorem, the Pythagorean identity. So here's our triangle. Imagine that this was created by the unit circle and a line going through that unit circle. So we know our hypotenuse is 1. We know that this is the change in the y values, and it's the sine of theta. We know that this is the change in our x values, and it's the cosine of theta. So using the Pythagorean theorem, we know that a squared plus b squared equals c squared. So in this case, that's x squared plus y squared equals 1 squared. But we know that x is cosine. And we know that y is the sine of theta. And we know that 1 squared equals 1. So if I rewrite this the same way that they rewrote it, I've got sine squared theta plus cosine squared theta equals 1. So that's why it's called the Pythagorean identity. Now, one of the things you'll notice in the way we write this, we do not write the sine of theta squared. That's not the right notation, so don't use it. The squared symbol is put above the actual trig ratio. So sine squared theta, cosine squared theta does mean sine theta squared. It's just the way the notation is written. All right, so the second property that's true of theta, and we talked about this before, is that the tangent of theta is equal to the sine of theta over the cosine of theta, rise over run. And the third one we also discussed before, which is for any line, y equals mx, which forms an angle of theta with the x-axis, the value of m, or the gradient of the line, is the tangent theta. So let's look at an example here. It says, find the gradient of the line which forms a positive angle of 130 degrees. So if we're looking for the gradient, we know that line goes through the angle. From our property up here, we know that the gradient is equal to the tangent of theta. So all we need to find is the tangent of theta. So the tangent of 130 degrees, we find that in our calculator, equals negative 0.1, oops, it's negative 1.19. That's it. Don't make this harder than it has to be. All right, next question. The gradient of the line shown, or find the gradient of the line shown in the diagram. So we notice here that our degree measure is 60, but we want to work with the degree measure that comes from the x-axis and moves counterclockwise. So that means if this is 60, this degree measure is 120. So we're looking at, when we look at the line that is intersecting the unit circle, we are looking at the theta that starts at the x-axis in the first quadrant, and then it rotates until we get to the line. So we don't use the 60 degrees, we use the 120 degrees. So to find the gradient, we would take the tangent of 120 degrees, and that equals negative 1.73. All right, so that finishes off 11.3. We'll do some, we'll do a couple more practice problems with that when we get to class, and then we will move on to section 11.4 in class. See you then.